Hello, my name is Xiao. I'm assistant professor from the Department of Industrial Engineering. After attending this workshop, I just modified the title of my presentation. I really like this one. So the original title was Physics-Based Statistical Modeling for Spatial Temporal Processes. So now I change it to Convergence of Physics and Statistical Learning for Spatial Temporal Processes. So I want to give you a little bit of background. So I started working on this problem 7 years ago when I joined IBM. So Yuan was my colleague when I was there. So at that time, I joined IBM. We worked with the Singapore government on a set of problems related to urban environment problems. For example, the modeling of urban air quality. So we developed both physics-based model and data-driven models to predict the air quality in the next 12 to 24 hours for Singapore as a service. And we also work on the tropical extreme weather events modeling and prediction based on a sequence of weather radar images. And we also work on the smoke dispersion modeling, because that's a major environmental problems in Singapore because of the agriculture related activities in neighboring countries like Indonesia and Malaysia. Okay, so let's make this problem more general. If you look at this data set, I think one thing that is sharing in common is that the underlying processes that generate this data can be described by partial differential equations, for example, like this. This is a typical, very general convection diffusion equations. So most of these processes are governed by equation like this or its variations. Now, of course, for those problems I briefly mentioned, we can use physical models to model the air quality. We can use physics models to model the rainfall processes. And there are certain advantages for using physics models. For example, we can use it to control, to monitor the process, to do planning, to do what-if analysis, because those models are based on physics. And during our collaboration with the Singapore government, we also realized that there are some difficulties if we just use physics model. For example, it's hard to generate real-time predictions because of the computational complexity. And it's hard to incorporate heterogeneous streaming data in real time if we just want to use physics. Because, for example, someone take a picture of the air quality, so we try to, if we want to incorporate that type of information into our prediction model, it's going to be hard to use physics-based model. And also, it's not very efficient or effective to use physics model to make short-term prediction because of the uncertainty associated with those model inputs and modeling uncertainty. Okay, and then we thought about statistical approach. So if you look at the literature of statistics, most of the statistical spatial temporal models are based on the construction of some random fields or random processes with specified space-time covariance structure to describe the data. And there are certain advantages of doing this. For example, it allows us to efficiently incorporate observations, data. And like many statistical models, those models allow us to quantify uncertainty quite effectively. And it's usually more accurate for real-time predictions and short-term predictions. So just use sensor data to make a short-term prediction. But also, there are some challenges and difficulties. One is model sophistication. For real complicated process, it's really hard to specify, for example, the covariance structure, the space-time covariance structure. If you think about how the pollutant concentration data are correlated in space and time, that covariance structure can change over time and space, given, for example, the wind conditions. And also, it's hard to interpret the results of a pure, data-driven model. And because of that, it's hard to use a pure data-driven model to do control, monitoring, and planning. And we have some physicists here, some geoscientists here, and statisticians here. I hope I didn't, make everyone angry about me by saying those things. But I think to a certain extent, we all agree that it would be nice if we can combine the strengths of physics model and data-driven approaches. So as a result, we're going to develop some physics-based data-driven spatial temporal models. If we can achieve that goal, that model should be able to incorporate basic physics. So if we can do that, the model can be more interpretable. The model will have a stronger predictive capabilities and so on. And in the same time, since it's a statistical model, this type of model should be able to incorporate observations. For example, data streams. This model should be very effective in terms of uncertainty quantification. And also, we hope this type of model can be computationally efficient so that we can use this model for real-time prediction and control. So these are some of the goals. Okay, so I want to use this one simple slide to summarize the idea that we have right now. We view statistical knowing as an optimization problem. Whether you want to build a linear regression model by minimize the least squares or you want to train a neural network. So we always have an objective function, and then we try to find the optimal parameters, search for the optimal parameters in a large parameter space. On the other hand, when we solve a physical model, when we solve those governance equations, we basically constrain the predictions or the physical model output to lie on the solution manifold defined by the law of natures. So those constraints we believe are very important, but are very often missing in traditional pure data-driven models. So as a result, we want to add those constraints developed from solicited from basic physics into the statistical models. So as a result, we're going to develop this physics-based statistical knowing as an constraint optimization problem. So the parameter space is actually much smaller when we consider physics in a statistical model. And if we can achieve that, we can make big decisions for high consequence applications to incorporate, the predictive power, interpretability, and domain knowledge into the model. And we can also leverage the traditional advantages, strengths of statistical model to do uncertainty quantification. And for certain applications, when data are sparse and expensive to acquire, for example, if you want to run a CFD model to generate some data, that usually takes time. But if we can develop like physics-based statistical model, we can use those statistical models as emulators or as surrogate models to quickly generate data for us. And so on. So as a conclusion, we often hear we let the data speak for itself. And our philosophy is we don't want the data speak for itself freely. So we want the data speak for itself based on the law of natures for physics or engineering domain knowledge intensive applications. And we have done some preliminary work. We're still working on this. I believe I'll be working on this in the following 5 to 10 years. So we have some early results about the modeling, which is under review. So Xiao there, he's one of my collaborators. And we're also using this type of model to do inverse modeling. For example, if we have sensor data, can we use this sensor data to figure out where the sources of the pollutants are, for example? That's one of the applications. And we have one paper published. And we also have some applications in different areas and with some US patents. And we're actively looking for collaborations. We want to try to see if this type of approach can be applied to different domains to solve different problems. So thank you.